In this presentation, we are going to focus on sensor mounting considerations and how best can you optimize your sensor mounting for the best frequency response and the best measurement. The first topic we're going to address is actually the sensor mass effect. You want to understand how much your sensor is going to influence the behavior of the structure under study. The dynamic properties of a structure are dependent on its mass, rigidity, and damping, as well as the way the sensor used for measurement is being attached to it. If the mounting of an accelerometer applies some additional mass to the structure, these dynamic properties can change. The resonance frequency, called here Fn in the formula of a structure, reduces approximately by delta F, where m is the mass of the structure of the unit under study, and ma is the additional mass from the accelerometer. One can see in this formula that if the mass of the accelerometer is negligible compared to the mass of the system, then delta F should be negligible. Regarding the vibration amplitude, A0, it can reduce approximately by certain amounts, A minus A0, depending also on the additional mass that's coming from the sensor. Once again, if the MA is negligible compared to M, the difference between the amplitude and the initial amplitude A0 should be negligible as well. How could we estimate that mass effect if we have no clue if the sensor can be negligible or not? Well, a rule of thumb can be to use a very simple excitation to generate a resonance frequency of the whole system, including your sensor mounted on it. First, you run a small shock test to excite resonance and measure with one selected sensor. Then, what you're going to do is apply an additional mass similar to the sensor mass. It could be a second sensor or a small piece that can be pretty much comparable. Then you would re-excite your system and redo a frequency response test and compare the two measurements. If there is a clear deviation, your sensor mass is too high. Then you should check carefully to ensure that the measuring data is usable and reproducible. Another alternative, if the sensor mass is too big and cannot be reduced, is to go for a non-contact method, such as a laser vibrometer we discussed in the first part. In the next slide, it's actually a small movie showing a very simple basic demo to show you how this resonance frequency can change due to the mass of the sensor. We are here performing a very simple test using a very simple demo setup made of cantilever's beam. We are mounting one of our piezo beam 8640A sensors, which is 3.6 grams, which is not really negligible compared to the mass of the beam. We are going to perform the shock test to excite resonance and look at the first two resonance peaks that are showing up at 80 Hz and 250 Hz. We then mount an additional mass to the system, which is comparable to the mass of the sensor, and look again at the resonance peaks. We see that the two first peaks did shift down to 70 Hz and 230 Hz. A lighter sensor is needed. We are now going to use one of our teardrop sensor, 8778A, which is 0.4 grams. And here you can clearly see that the first peak is actually shifted higher at 90 Hz, and then the next peak is much lower and much further. The sensor mass here can be assumed as negligible. Now that we've seen the influence of the sensor mass itself, we're gonna look at how to mount as best as possible a sensor to avoid any major influence on the measurement you're performing. You need to be aware that anyway, depending on the mounting types you're gonna use, you're gonna lose in frequency response. Here are the most common mounting types you can encounter out there, starting from the probe, then going into magnetic mounting using a magnet, so that's only for ferromagnetic surfaces, then doing adhesive mounting, direct adhesive sensor on the surface, or eventually using an adhesive mounting base, and the stud mounting. Those are represented in order of greater coupling rigidity, meaning that stiffer coupling will be entered by stud mounting, and softer coupling is of course a probe. First in line for the most rugged, stiff mounting you can do, the preferred method would be stud mounting. This is possible with sensors that have integral stud or a thread to screw on a stud. Then we are using that method to calibrate such sensors because that's where you get the best frequency response. When mounted with stud mounting, you can use a standard stud, or you could eventually use an isolated stud that has an integral plate in between the sensor and the mounting surface. Most of the studs are aluminum anodized. They are adding a little mechanical filtering, a little bit of mass maybe, but not that much. So you will see later that they have low influence on the frequency response. Whenever stud mounting the sensor, the coupling surface must be as smooth, flat, and clean as possible. With higher frequency from about 2 kHz, it is beneficial to also have a thin film of oil or grease between the coupling surfaces. You will see in the next slide the tightening torque of the sensor is usually very critical. You should use a calibrated torque wrench of a suitable design. Before mounting the sensor, if you are doing a mounting where you are required to have isolated stud, you always need to check that stud for damage. Heavily anodized aluminum studs may be scratched and no longer insulate adequately. On the other hand, if you use studs with ceramic inserts, depending on the design, you may have not adequate transverse rigidity, and it could be also that the upper temperature limit can be very critical in such cases. As mentioned, you should use a torque wrench. Usually in the datasheet of a sensor, we recommend you torque to mount your sensor with the appropriate stud. If the torque is lower than the one recommended, what can happen is that you have a moving system where that would lead then to a lower resonance frequency. On the other hand, if you over torque, then you can damage the stud, and more importantly, you can damage your sensor itself. And sometimes it happens that, for example, isolated ground isolation bays are being removed and broken off because of over torqued. Next in line with the most rugged mounting is the adhesive mounting. Can be first direct adhesive mount using, for example, wax. This is the case if you do calibration of sensors or possibly modal analysis at lower G amplitudes. Then it could be adhesive mounting base used because, first of all, you don't want to have any damage to your sensor base if you need to scratch off the adhesive. And second of all, it's usually the case for people that want ground isolation. And in that case, those bases are made of aluminum. Here in this table, we are giving you some example of adhesives that can be used. Whatever adhesive you choose, remember to always use a thin layer as much as possible to avoid any damping that could then lead to a lower frequency response. The first in line are temporary removable methods like the wax, the double-sided glue tape, thermostatic plastic glue tape, high-tensile silicone flash masking tape. We are then telling you where it can be used, which mounting area, what are the temperature it can be used at, what availability you can have from which manufacturer, and what kind of solvent can be used for removal of it. The next will be the fixed, removable, or permanent glue, hot glue, super glue that can be used, and what are their temperature limitation. And last but not least, the permanent method you can use for mounting at higher temperatures. Magnetic mounting is also well appreciated whenever a ferromagnetic surface is involved. It's appreciated because it's very convenient. You can move around the sensor very quickly. The thing is that magnetic mounting is very heavy, so that can affect a lot the frequency response of the sensor. And in addition, it's very dangerous for the sensor itself. Whenever a magnet is being used, we recommend first to mount the magnet on the surface and then the sensor on the magnet. And if this is not possible, we recommend to be very careful and approach the surface with an angle as it's being shown in the little drawing here. Try not to just drop the sensor and magnet on the surface, because such a sharp metal to metal impact can be deadly for the electronic inside the sensor. We have discussed a different recommendation for mounting a sensor and the way to use those different mounting options, but what we would like to show you now is an illustration of those recommendations and also how this can affect the frequency response of your measurement. So this was a test we've done in our tech center. We were using a calibration shaker in our tech center in Shanghai with the dedicated calibration software that allows for calibration from 10 to 10,000 Hz, showing the sensitivity deviation and the phase. We are using an 8702 B500 quartz-based sensor that is being mounted in different ways on the shaker. We then run a frequency sweep from 10 Hz to 10,000 Hz, and we will look at the sensitivity deviation and the frequency deviation. First, we will mount the sensor using grease and a stud. So we will screw down the stud and then apply the grease. Then we will mount the sensor onto the shaker and then fasten using a torque wrench at 2 Nm. Then we will mount the cable on the sensor and fasten the cable as shown here. Then looking at the frequency sensitivity deviation, we can see a 5% deviation at 10,000 Hz. Now using the wax, we want to soften the wax into our finger The goal here is to make a thickness of wax as thin as possible. So we'll cut around 3 small pieces of wax, not to have too much on the sensor. Then you press and twist. In that way, the sensor is securely fastened and there is no moving around during the frequency test. Looking at the results, we have a 5% deviation up to 4,000 Hz. In that way, we are using wax again, but this time we are using an isolated mounting base. And once again, we are going to apply 3 small pieces of wax. Screw down the sensor using the torque wrench again. Don't follow my lead here. We press and twist to have it fasten on our shaker, and then we run the test. And here we're gonna see a deviation of 5% to 2000 Hz. So the frequency response is getting lower and lower, adding those mechanical filters in between the sensor and the surface. Now, this is a bad example. We put way too much wax at the bottom of the sensor, plus we have this base. So we have 2 major mechanical filters in there. Here we'll see that the response at 5% will then only be at 1600 Hz. So if we here look at the results, we'll see that basically the best response is being obtained with stud only, well, stud and the silicone, which is a green curve with very flat response up to 10,000 Hz. Then when we start using the deviation, using the wax, then we see that we start seeing already the beginning of the resonance pulse with the purple curve. Then the next one in line will be using adhesive mount using an isolated plate, which is a blue curve. And then the last one is using this isolated plate but using way too much wax. So you can see that the mounting can really affect the frequency response of your sensor, but at the end of the day, the optimal way of mounting the sensor will always be the stud mount. Here, it's basically a summary of what we just discussed. So, from the left to the right, we have the softer mounting to the stiffest mounting. So, whenever we calibrate a sensor that can be stud mount, we always stud mount that sensor. So that's the purple line you see, number 6, the mounting type number 6. It's the best frequency response you can get. Then, if you are using an isolated stud, so this plate is all integrated in one piece with the stud, that's the one you see between 5 and 6, you should get a peak that is fairly close to the stud mounting. Just a little bit lower because you have this additional plate in between playing the role of a mechanical filter, but it's minor. Then, you have the direct adhesive mounting using glue or very, very thin layer of wax. So this should be giving you the peak number 5. So it's still a good performance. Of course, not as good as the stud mount. Then, next one will be number 4, the adhesive mounting base usage. So in that case, you use a stud and a separate plate, or something that is all integrated together. This adds some mechanical filtering in there, so you can see that your frequency response, which is in green here, will start its resonant frequency peak much sooner. Then we have the number 3, magnetic mounting. This is mostly due to the weight of the system. Here you are very limited toward the low frequency response. It's the yellow curve. Then number 2, using the magnetic base, and you put a foil in between that can be for isolation, for example. Well, once again, you add an additional mechanical layer, so you reduce again your frequency response, so it will be the red one, number 2. And last but not least, using a probe, you'll be in the black case, number 1. The example we showed you before are just example using a specific sensor with a specific mounting base. So in each case, it's very useful to really investigate your own mounting configuration with your own sensor and your own mounting base and run a frequency response test to have an understanding of your resonance peak, and then consider that basically your frequency response plus minus 5% will be somewhere around 25% of this first resonance peak value. Now, in the investigation I showed before, we were using a shaker. Well, a shaker doesn't have to be used. You can also perform a simple resonance test doing a very short impulse, using a breakage of a lead or just tapping around the sensor with a very, very small screwdriver. Generating a very sharp pulse will excite the full frequency spectrum. So then you just need a scope with FFT or a data acquisition system with FFT and look at the frequency response of your system to see what is the first resonance peak. The resonance test is really useful in general. It can also tell you a lot about the sensor functionality, the quality of the sensor mounting, that's what we talked about, and whether if the sensor is properly connected and the cable is working and so on. This procedure can be applied to all sensor types, but caution may well be necessary for piezoresistive sensors because of the high quality. With this procedure, the sensor is... In the video I showed you earlier, we were seeing that we were fastening the cable using a piece of tape on the shaker. We absolutely need to fasten cable to minimize cable movement and avoid any active forces or shock that can then come and stress the cable itself, but also the connector of the sensor. That can influence your measurement, but that will also lead to sensor breakage. So the cable needs to be fixed to the vibrating surface, and when you do fasten, avoid any stress. So try to have kind of a loose loop and so on. This is a drawing which is an extract from the ISO 5348 that are providing recommendation for cabling. So to summarize, always take the cable to the sensor and attach it, never the other way around, to avoid any pin damage. Attach the cable connector sufficiently firmly so that it cannot come free during the measurement. It's recommended to fix the cable in position after no more than 50 or 75 mm of cable length to minimize the cable vibration. Whenever you have damp environment, I will mention that in the next slides, always some protection on the connector, like shrink tubing and things like that. Always keep connectors clean to maintain the high insulation resistance to ground whenever we are talking about charge output sensor. In general, connector needs to be kept clean anyway. and handle the cable just as carefully as the sensor. In some cases, we have very harsh environments that could lead to dust, or that could lead to some steam or some water spray and so on. It's very important to understand what is the case sealing of the sensor, but also what is the tightness, IPL grade between the sensor and the cable. First of all, when you look at a data sheet, it will tell you if a sensor housing is hermetically sealed, or what they would call environmentally sealed or epoxy sealed. The hermetically sealed housing means that the housing is welded. This is the case you can see here for the gray housings that are made of stainless steel or titanium. The connector is also glass, ceramic, metal, and it's sealed. If we are saying in data sheets environmental sealed, it also means epoxy sealed. It means that the sensor case assembly is not fully welded or not welded at all, and it's more about putting it together using epoxy. In that case, you are not watertight. Once again, we are here talking about the housing sensor case only and not about the junction with the connector. Here is about the junction of the connector. You have 4 possible levels of tightness against external influences. You could use shrink tubing, like the Reicham shrink tubing DR20. So you would use it over the connection between sensor and cable. You can also have example of splash-proof or waterproof connectors. Then you have sensors that are completely waterproof, IP68, and tested under pressure, under water, up to 10 bars. If you really want to use a sensor underwater, that's the kind of certification you need. And the fourth option is some kind of waterproofed cable. So once again, in that case, it's not integral cable anymore, such as example 3. It's a separate detachable cable, and there too, if you want to use it underwater for a certain duration in time, you need a specification and a qualification that shows that this solution has been tested under pressure and had a certain level, such as 10 bar, 14 bars for 3 days or so. Once again, thank you very much for your attention here. We recommend you to follow the next course, which is about troubleshooting and how to figure out if a sensor is still alive. We also recommend you, if it's not already done, to also follow the other 2 presentations about sensor technology and about sensor specification and datasheet understanding.